Alrighty. Einstein is famous for his theories of special relativity and general relativity. They're called relativity. We're going to be talking about relative motion, two objects moving relative to each other. Up until now, we've only looked at one object moving at a time. Now we're going to say, hey, what if you have two objects moving? Well, how they're moving depends on what you want to choose as your reference point. The reason one's called special relativity, it should really be called special case relativity. And the special case, Parker's going to put his phone away before I completely take it away. Special case is that, you can write this down, acceleration is going to be 0. General relativity, acceleration is not 0. General relativity took Einstein 10 years to prove. Special relativity we can prove with Math 8. So we're going to start off with what we call thought experiments. Einstein was very good at coming up with thought experiments. And here's the first one. I'd like you to imagine that we have a cannon that can launch a baseball at 30 meters per second every time. So situation number 1, here's our cannon. Sam is the target. He's holding a baseball glove and he's standing still. We fire the cannon. Boom!
Oh. B.
How fast will the baseball be traveling when it reaches Sam? Let's ignore air resistance. So how fast will it be going? It will be going 30 meters per second. And that's because right now we only have one thing moving, the baseball. Now let's put the cannon on a truck, on the back of a pickup truck or on the roof of a van. The van is traveling towards Sam at 15 meters per second. So this V is the van traveling. Boom! We also fire the cannon. What was that? Okay. Situation 3. What if we're moving the van away from Sam at 15 meters per second? Headphone out, please, Lyle. And we fire the cannon, boom, at 30 meters per second. How fast does Sam see the ball arrive at? 15. Hey, what if we had the van going that way at 30 meters per second and we fire the cannon backwards at 30 meters per second? Put your pencils down and look up.
Whoa.
Yeah, what?
You can do it with a human being, but with a soccer ball is a little safer.
We're gonna see that ball drop.
So Mythbusters looked at this.
Momentum matched as close as they're going to get it. The pressure's on Grant for a perfect release.
I don't know about you guys, that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my god, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that. Fantastic. I mean, look, it doesn't move at all.
So yeah, you fired it backwards at 30 while the van was moving forwards at 30. The relative velocity of the ball to us would be 0. Okay? The people on the van would see the ball moving backwards, but it's actually because they're moving forwards. Okay. Now let's go cosmic. This is one of the most famous experiments in physics, the Michelson-Morley experiment. In the late 19th century, in about 1890, two physicists, Michelson and Morley, conducted an experiment in the same way that when the baseball was moving towards Sam, the velocities added, and when the baseball was moving away from Sam, the velocity subtracted. They thought they could do this with the speed of light. Now, the speed of light is crazy fast, and so moving a flashlight on a van, you're not going to notice the difference. But they thought the Earth moves around the sun pretty fast. They thought they would measure the speed of light when the Earth was moving towards a distant star, and they would measure the speed of light when the Earth was moving away from a distant star. And in the same way as we got a 15 and a 45, they thought we should be able to measure that ever so slight difference. Got the argument? Okay. So they thought they could measure the difference in the speed of light hitting the Earth in two situations. The speed of light hitting the Earth when the Earth was moving toward the light source. The speed of light hitting the Earth when the Earth was moving away from the light source. Here's a picture of what they wanted to do. And they had designed an apparatus that they thought could pull it off. So in January, the Earth was moving toward the star with a speed, we'll call the speed u, relative to the sun. We call the speed of light c, so they figured that they would get an answer of c plus u, the 45. In July, the Earth was moving away from that distant star, and so they figured that they would get c minus u, the 15. So they did the experiment, and that's not what they found. They got the same answer both times, the same speed of light both times. This would be like the baseball question, Sam having the baseball arrive at 30 each time, no matter what. Huh? And here's the conclusion. Light is special. And when you measure the speed of light, it will be a constant for all observers. Anytime you measure the speed of light, whether the light source is moving towards you or away from you, light does not behave like the baseball. You will always get the same answer, always. The Michelson-Morley experiment is famous for its negative result. It showed experimentally that the speed of light in space through a vacuum is the same for all observers, regardless of their velocity or the velocity of the light source. The speed of light does not depend on your frame of reference at all. They could not find any evidence that space could be used as some kind of fixed frame of reference. So the speed of light is a constant. What letter does the word constant begin with?
C.
We use the lowercase c as our symbol for the speed of light because it's the constant. If you're wondering, it's 3 times 10 to the 8th meters per second. It's pretty fast. So what does that mean? We're ignoring acceleration. I said that a was 0, so don't write this down. Instead of d equals vit plus a half at squared, a is 0. We have just d equals vt. Let's get the v by itself. How would you get the v by itself? So we would get this. Speed is distance over time. Or better yet, let's go cosmic. Speed is space over time. How can we always get the same answer no matter what's going on? The only way that we can always get the same answer is if space and time change depending on the situation. Spencer's going to completely put his phone away because this is profound. Put your phone on the desk behind you on the desk there, please. Yeah, all the way back there. Thank you. Put your pencils down, look up.
There are only a handful of experiments in physics that completely physicists thought that
Sorry.
At many
Let's try that
only a
again.
handful of experiments in physics that completely transformed physics. At many people's top of the list would have to be the Michelson-Morley experiment.
In the 19th century, physicists thought that since sound waves travel through air, light waves must travel through some sort of medium as well.
So sound needs air to travel. There's no sound in a vacuum. There's a famous movie slogan that says, in space, no one can hear you. You all know the punchline, right? In a vacuum, sound needs something through which to travel. And since light is a wave, they thought that space couldn't be a vacuum. They felt it was filled with something. You can see the word on the screen behind me that they called the ether.
They called this theoretical medium ether.
The famous luminiferous ether. This magical medium that was hypothesized to be what light required to move through the vacuum of space, just the way sound requires air to move from one place to another. How else could waves of light move through the vacuum of space unless there was some medium there, some hypothetical medium? Let's call it the ether.
Ether, they theorized, is an invisible nothingness that permeates the universe. Its only physical property is that it allows light to propagate through it. But once precise measurements of the speed of light became possible, testing the predicted effects of ether on the speed of light became possible as well. The Earth orbits the Sun at about 66,500 miles per hour. If light travels through ether, they reasoned, then as the Earth moves through the ether, the speed of light should be different going with the ether than perpendicular to it. In an attempt to show the effects of ether on the speed of light, Albert Michelson and Edward Morley conducted an experiment in 1887 at what is now Case Western Reserve University.
Michelson was an expert in optical experiments, and he thought that he could devise an experiment where one would be able to see the slight difference in the speed of light measured on the Earth if you measured it along the direction of the motion of the Earth and at right angles to it.
So how do you measure that slight difference? Very cleverly, here's what they did.
There should be a slight difference.
Compared to the speed of light, Earth is not moving that fast. So if you're going to check the difference in the speed of light, measured with the movement of the Earth compared with transverse to it, you need a level of precision that no one had before. The Michelson interferometer was just such an apparatus.
Michelson and Morley devised an apparatus that would detect minute differences in speed between two beams of light. Light from one source is split into two directions through a half-silvered mirror. These beams are bounced between other mirrors and then recombined back into a single beam.
So we're going to take a beam of light, we're going to split it. Let's suppose the Earth is traveling to our right. Well, then this beam of light should have the Earth's speed added to it. This beam of light shouldn't. And so when you recombine them, they should be ever so slightly offset. Got the argument?
When two light beams combine, if their waves are completely synchronized, the peaks combine to make an even more intense peak. If they are one half wavelength off, their peaks combine and cancel out the intensity. Slight differences in speed between two light waves will therefore produce a pattern based on the amount of interference between the two beams. This is known as an interference pattern. Examining the interference pattern from the two light beams sent out in different directions would clearly show if the speed of each light beam were different in
So they were expecting, can you see really close that ever so slight mismatch? That would tell them that there was a difference in speed, and by measuring that mismatch, you could calculate what that speed difference was. That's the result that they were expecting.
different directions. But Michelson and Morley never detected such a difference.
The beams of light were matched up perfectly. No speed difference.
Their results were inconsistent with the existence of ether.
The scientific world didn't know what to make of it. The famous scientists in Europe, all Lord Rayleigh and Lord Kelvin and Lord Thomson, were saying, hey, come on, you must have done something wrong here. There has to be an ether. And the whole thing didn't get resolved until many, many years later when Einstein came along.
Einstein's theory of special relativity proposed that the speed of light is always the same, regardless of the speed of the light source. The results of the Michelson-Morley experiment were entirely consistent with Einstein's view of the universe, and this served as the turning point in modern physics.
The Michelson-Morley experiment was an experimental advance in technology that transformed science. Not only physics, but science.
Why? Let's keep going. Consider the following situation. Suppose we have a spaceship that's emitting a flash of light. We're going to use the light flash as our timer. Why are we going to use the light flash as our timer? Well, light's the thing that's behaving weird. So why don't we work it into our experiment? Situation number one, the spaceship is hovering at rest relative to the Earth. It's going to send out a flash every 6 minutes. Flash. 6 minutes later, flash. 6 minutes later, flash. It'll take a little while for the light to reach the Earth, but once it reaches the Earth, the person on the Earth is going to see a flash every 6 minutes. Flash. 6 minutes, flash. 6 minutes, flash. And so when the spaceship is at rest, and the Earth is at rest, they don't notice any difference. Now let's get this spaceship moving really fast. So first of all, in 60 minutes, if we send a flash out every 6 minutes, how many flashes will the ship send out in 60 minutes? Do the math, hopefully, in your head. 10. How many flashes will the people on Earth see in 60 minutes? So both of them would say that event took 60 minutes. 10 flashes, 60 minutes. Situation 2. When motion is involved, the situation is very different. Now, it's important to note that the speed of those flashes will still be the speed of light. This is what Einstein said. He said light's not going to behave like the baseball. It's always going to travel, not at 15, but at the speed of light. Not 45 and not 30 and not, I said 15. It's going to travel at 30. It's not going to travel at 15 or 45. It's always going to be the same. However, how frequently the flashes are seen, however, that does depend on the relative motion involved. When the ship travels toward the receiver sees the flashes more frequently. This happens not only because time is altered due to motion, but also because each succeeding flash has less distance to travel, because the ship is getting closer and closer and closer. So let me give you a picture here, all right? This spaceship is moving this way really fast towards the Earth. On the spaceship, someone is looking at their watch, and every 6 minutes, flash. Every 6 minutes, flash. But because they're getting closer and closer, they're catching up to the flashes are bunching up. On the Earth, they're seeing the flashes arrive only 3 minutes apart. 3 minutes apart. 3 minutes apart. 3 minutes apart. So in 60 minutes on the spaceship, they'll emit 10 flashes. And they would say 10 flashes took how long? 60 minutes. But the flashes arrive on the Earth 3 minutes apart. How long will 10 flashes take to arrive on the Earth? The same event on Earth would be measured as having taken 30 minutes. But on the spaceship, they would tell you, oh, no, it took 60 minutes. Let's look at this some more. Suppose the spaceship is going away from the Earth really fast. Because the distance for each flash to travel is increasing, even though the spaceship is sending a flash every 6 minutes on their clock, they're arriving on Earth, let's say every 12 minutes. We'll have them go at just the right speed so that the flashes arrive every 12 minutes. So again, two events that are separated by 6 minutes according to the spaceship will be seen to be separated by 12 minutes when the spaceship moves. Instead of moves, let's say retreats, goes away at a very high speed, and every 3 minutes when it approaches at a very high speed. This event, the Earth would say, 10 flashes took 120 minutes. But the people on the spaceship would say, no! 10 flashes took 60 minutes. Same event, different time passing for the events. You can illustrate this with what we call the twin paradox. If you have identical twins that are the same age, let's make one an astronaut. I'll call him twin A for astronaut, or her twin A for astronaut. They're going to take a high-speed round-trip journey. They're going to go away really fast and come back really fast. Twin H stays at home. H for home. When the traveling twin returns, he or she is actually younger than the twin that stayed home. How much depends on the speeds. Let's look at this here. So we have a picture here. Here's our sending a flash every 6 minutes while the spaceship is going away, receiving a flash every 12 minutes back on Earth. Spaceship turns around, starts coming back towards the Earth. Now the spaceship will see the Earth will see the flashes arrive every 3 minutes. Let's look at this light clock and let's walk through it and see what happens. We're going to apply this doubling and halving of flash intervals to the twins. So suppose the spaceship goes away for 1 hour, instantly turns around and comes back for 1 hour. We're going to follow this line of reasoning with the chart on the next page. The traveling twin will take a trip of 2 hours according to all the clocks on board the spaceship. Spencer, you want to stay off your watch as well? Thank you. The trip will not be seen to take 2 hours relative to the Earth. Let's fill this chart out together, already? I'm going to zoom in on the next page so you can see easier. And we're going to do, first of all, the clock on board the spaceship all the way till the end of the trip. And then we're going to do the clock back home on Earth. So you ready? The first column is the spaceship clock. Let's have them leave at noon. After 6 minutes, they send a flash. Flash. 6 minutes later, they send their second flash, and they note that the time for that is 12:12. Flash. Now they note the time is 12:18 for flash number 3. Flash. Now they note that the time is 12:24 every 6 minutes. Flash. What time will they send the next flash off at? Flash. 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 In box number 9, flash. Box number 10. Instead of 1 o'clock, let's go 1300 because that's going to make the math easier. Now the spaceship turns around and is heading back to the Earth. So we're going to go to the next column, top of the page here. In column 11, still every 6 minutes, 1306. Flash. 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 13. Flash. 13. Flash. And when the astronaut lands back on Earth, the clock on their ship would read 1400 hours. How much time has passed for this astronaut? Now, what would happen on Earth? Well, first of all, initially the astronaut is retreating from the Earth, which means the flashes take longer to get here. So Earth would see the first flash at 12:12. Flash, 12:24. 12:36. Flash, 12:48. Flash, 1300. Flash, 1312. Flash, 1324. 1336. 1348. And then we get 1400 hours. But now the spaceship turns around. Now that it's coming towards the Earth, because it's getting closer and closer, the flashes have less and less distance to travel. So now they start to arrive every 3 minutes instead of every 12 minutes. And so now it's going to see the next flash at 1403. Flash, 1406. Flash, 1409. Flash, 1412. Flash, 1415. And remember, on Earth, we're setting our watch according to these flashes. Flash, 1418. Flash, 1421. Flash, 1424. Flash, 1427. Flash, when the astronaut arrives back home and he runs up or she runs up to his twin or her twin and they compare watches, The astronaut, the twin back home, their watch would read 2:30 in the afternoon. The astronaut would read 2 p.m. The astronaut has experienced 30 minutes less time than people back home on Earth. The astronaut has traveled through time. Time travel is totally doable. Before I take your question, this is the long way. Is there an equation where you can just jump right to the answer? Yes, and we'll derive that on Thursday. There is an equation. But this is how the universe works. As soon as you start to move relative to another object, time is moving different for you, slower for you. So right now, I'm going to start to walk around the room for a second. Right now, you can prove I am aging slower than you are. Time for me is moving slower than it is for all of you because I am moving relative to you who are at rest. Now, I'm moving so slowly, it's not measurable. You can calculate it with a good calculator. But if I was going near the speed of light, oh, heck yeah. Yes, oh, heck yeah.
That's science. Using that logic,
Yep.
they compared their watches.
Yep.
Isn't 60 seconds in space the same as 60 seconds on Earth?
60 seconds in space is the same as 60 seconds anywhere if both objects are at rest relative to each other. But if one object is moving relative to the other object, they do not experience. Time does not flow the same.
So the watch, even though it ticks like at the same rate, like 1 second.
The heartbeats would be different, the aging would be different, the cellular processes would be different, the electrons would be moving slower in their orbitals around the atoms. Time would move different for a moving object compared to a non-moving object.
How do you know?
We're going to prove it next. And we've measured it many, many, many times. For example, GPS satellites move faster than the Earth in orbit. We have to correct for the fact that the atomic clocks on them are actually experiencing time slower than us on Earth's surface. If we didn't, GPS would be out by about 2 kilometers a day. We measure this all the time. When we're doing very, very fine machining, fine engineering, we have to take Einstein into account. So next class, we'll see if there's a way to calculate this time differential with an equation. There is. So is it possible to travel through time? Yes and no. It is absolutely possible to travel into the future. Easy peasy. Just go really fast and come back. And time will have moved slower for you, and so you will end up, when you get back, in their future. But we're pretty sure you can't travel into the past. I will later on show you one possible theoretical way that might work, but we also think that once we have the physics to be able to actually do that, we'll have discovered new physics that says it won't work.
Are you able to speed up your aging? Like move so slow, like move negative slow? I guess I'd be moving into the past, yeah.
Have you ever daydreamed about travelling through time? Perhaps fast forwarding the centuries and seeing the distant future? Well, time travel is possible, and what's more, it's already been done. Meet Sergei Krikalev, the greatest time traveller in human history. This Russian cosmonaut holds the record for the most amount of time spent orbiting our planet, a total of 803 days, 9 hours, and 39 minutes. During this stay in space, he time travelled into his own future by 0.02 seconds. Travelling at 17,500 miles an hour, he experienced an effect known as time dilation. And one day the same effect might make significant time travel to the future commonplace. To see why moving faster through space affects passage of time, we need to go back to the 1880s, when two American scientists, Albert Michelson and Edward Morley, were trying to measure the effect of the Earth's movement around the Sun on the speed of light. When a beam of light was moving in the same direction as the Earth, they expected the light to travel faster. And when the Earth was moving in the opposite direction, they expected it to go slower. But they found something very curious. The speed of light remained the same no matter what the Earth was doing. 2 decades later, Albert Einstein was thinking about the consequences of that never-changing speed of light. And it was his conclusions, formulated in the theory of special relativity, that opened the door into the world of time travel. Imagine a man named Jack standing in the middle of a train carriage travelling at a steady speed. Jack's bored and starts bouncing a ball up and down. What would Jill, standing on the platform, see through the window as the train whistles through? Well, between Jack dropping the ball and catching it again, Jill would have seen him move slightly further down the track, resulting in her seeing the ball follow a triangular path.
So this is why we call it relativity. Jack's point of view, relative to Jack, he sees the ball moving straight up and down. Jill, sitting on the side of the road, also sees the ball traveling sideways while it's moving up and down. So she sees it kind of trace out this V path. As far as she's concerned, the ball traveled a longer distance than just straight up and down.
This means Jill sees the ball travel further than Jack does within the same time period. And because speed is distance divided by time, Jill actually sees the ball move faster.
Okay, that's how the world works. Except now let's replace the ball with a beam of light bouncing up and down.
But what if Jack's bouncing ball is replaced with two mirrors which bounce a beam of light between them? Jack still sees the beam go up and down, and Jill still sees the light beam travel a longer distance. Except this time, Jack and Jill cannot disagree on the speed.
So instead of getting different speeds, the universe says they have to end up with the same answer. How can you do that with different distances? They must have experienced different times. They must have seen the same event, but time moved differently for both of them.
Because the speed of light remains the same no matter what. And if the speed is the same, while the distance is different, this means the time taken will be different as well.
They saw the same event, but if you asked Jill how long it took on the left a really small number because it's a really short event. If you asked Jack how long it took on the right. And there is no experiment that you can do that would show that either of those answers is the right one or the wrong one.
Thus, time must tick at different rates of people moving relative to each other. Imagine that Jack and Jill had highly accurate watches that they synchronized before Jack boarded the train. During the experiment, Jack and Jill would each see their own watch ticking normally. But if they meet up again later to compare watches, less time would have elapsed according to Jack's watch, balancing the fact that Jill saw the light move further.
Their watches would no longer be synchronized. We have done this.
This idea may sound crazy, but like any good scientific theory, it can be tested. In the 1970s, scientists boarded a plane with some super accurate atomic clocks that were synchronized with some others left on the ground. After the plane had flown around the world, the clocks on board showed a different time from those left behind.
The atomic clocks were no longer in sync because the plane was moving relative to the atomic clocks at rest on the Earth. The plane, the clocks, the pilots experienced less time than the people and the clocks that were at rest on the Earth.
Of course, at the speed of trains and planes, the effect is minuscule. But the faster you go, the more time dilates. For astronauts orbiting the Earth for 800 days, it starts to add up. But what affects humans also affects machines. Satellites of the Global Positioning System are also hurtling around the Earth at thousands of miles an hour, so time dilation kicks in here too. In fact, their speed causes the atomic clocks on board to disagree with clocks on the ground by 7 millionths of a second daily. Left uncorrected, this would cause GPS to lose accuracy by a few kilometers each day. So what does all this have to do with time travel to the far distant future? Well, the faster you go, the greater the effect of time dilation. If you could travel really close to the speed of light, say 99.9999%.
So let's suppose you got a spaceship that was going at 99.99% of the speed of light, and you traveled for 1 year, 6 months out and 6 months back. Time is moving so much slower for you that on your spaceship, it would be the year 2022. On Earth, it would probably be the year 2400 or 2500 or more. And that is time travel into the future.
On a round trip through space for what seemed to you like 10 years, you'd actually return to Earth around the year 9000. Who knows what you'd see when you returned? Humanity merged with machines, extinct due to climate change or asteroid impact, or inhabiting a permanent colony on Mars. But the trouble is that getting heavy things like people, not to mention spaceships, up to such speeds requires unimaginable amounts of energy. It already takes enormous particle accelerators, like the Large Hadron Collider, to accelerate tiny subatomic particles to close to light speed. But one day, if we can develop the tools to accelerate ourselves to similar speeds, then we may regularly send time travelers into the future, bringing with them tales of a long-forgotten past.
So time travel, totally doable. What if you went faster than the speed of light? Well, wait a minute, Mr. Dewick. I thought you couldn't go faster. I thought light was the cosmic speed limit. You can't go faster than the speed of light in a vacuum, but you can go faster than the speed of light traveling through a different substance, and you get something really cool.
All right, here's a funny question. So this is from Jeff Sloan. And Jeff says, just an interesting thought that I had that I would like you to explore or completely debunk. If objects moving faster than the speed of sound can cause a sonic boom, is it at all possible that the Big Bang was a result of something traveling faster than the speed of light? If I'm correct, please provide an address where I can pick up my Nobel Peace Prize.
Okay, first of all, the Peace Prize is not given for discoveries in physics. That would be the Nobel Physics Prize.
Aha!
Just to clarify that.
There you go, Jeff. Sorry, buddy. No Peace Prize for you, no matter what.
No matter what. Occasionally a scientist can win a Peace Prize, but it's rare. It usually goes to a politician in power.
Right.
Or a dissident in power.
Right.
Right. So anyway, so he wants to know if you can get a sonic boom, a light boom. Yes.
Basically a light boom is what he's talking.
The answer is yes. It's called Cherenkov radiation.
Dude, you are killing me.
Yeah. Yes. If you travel faster than light, there is the light equivalent to a sonic boom, where the light pulse builds up on itself, and there's a flash of light, and it's called Cherenkov radiation. Now, but since you can never travel faster than light,
right,
you might ask, how does one come up with this stuff?
Exactly.
Here's how it works. If you have light traveling through water, transparent water, light travels slower through water than through a vacuum. It travels, so let's start this. It's fastest in a vacuum.
Right.
Travels a little slower going through air.
Right.
Travels a little slower going through water.
Right.
Travels even slower going through glass. Travels even slower going through diamond.
Okay. And of course that is because it is both a wave and a particle.
Yeah, it's trying to get through the medium. And in fact, the diamond, I remember my number, is 40% as fast in a diamond as in a vacuum.
Wow.
Yes, it's
That's
slow.
a huge difference.
That's what makes diamonds so cool. So if you put facets in the diamond at the right angles,
right,
at the correct angles, because the right angle would be 90 degrees, at the correct angles, because what we call the index of refraction is so large, because light travels so slowly in a diamond, that it bends back on itself multiple times within the angles that you can create on your ring, and then it shows up again in a different direction. So that's why a diamond looks like it sparkles. Because if it was only light coming from where the light came from, you say, oh, that's just the light I'm looking at. But if it comes from a new angle, you say, hey, that diamond is sparkling, is talking to me.
Right.
So, all right, so now you have light going through all these media. Now you send a particle through there faster than that speed. That will create a mini sonic boom, except it's not sound, it's light, a mini light boom. And it was first described by the physicist named Cherenkov, and he won a Nobel Prize for this discovery.
Look at that.
Cherenkov. So tell him the Nobel Prize has already been.
It's already been. Sorry, Jeff. Your prize has been claimed.
Okay.
You were right, but somebody beat you to the punch.
Wait, but let me get back to the Big Bang. So the Big Bang was an expansion of the universe faster than light, but it's not the universe expanding faster than light in a medium.
Gotcha.
It is the very fabric of space and time itself expanding, and you don't get Cherenkov radiation from
that. Okay, right, because it's actually happening in the vacuum, which is space.
Well, no, I mean, all of space is the explosion. It's not a vacuum within the space.
Oh, okay, so the space itself is the explosion.
Is the explosion.
Gotcha.
Duh.
Look at that. That's awesome.
Right, okay.